Good afternoon, everyone. I'm glad to have you here in today's class. The topic that we are going to be looking at is entropy. In thermodynamics, entropy is defined as a measure of degree of disorderliness, randomness, and unavailability of energy in a system. The SI unit of entropy is Joule per Kelvin, and it can also come in the specific form as Joule per kilogram Kelvin. Entropy can be expressed in the mathematical form as change in S equals to change in Q over T, where change in S is defined as the entropy change the Q is the amount of heat transfer in the system, and T is defined as the temperature in Kelvin. Characteristics of entropy. 1. Entropy increase in a given system occurs as a result of when heat is being transferred into the system. The second characteristic is entropy decreases when heat is being removed from the system. The third one, entropy becomes zero when we have a reversible adiabatic process, which is also known as isentropic. Now, what are the key features of entropy? The features come in two different categories. One, the process that increase entropy. And the second one is a process that decreases entropy. So let's look at an example of such processes that increases entropy. The first one is when you melt an ice. In such case, you are transferring heat to the ice. For example, you know that ice come in the form of a solid state. When you are trying to change the state of that ice to liquid or gas, which means definitely you are doing what? You are adding heat to it. That is why I said earlier that an entropy increase as a result of what? It's being input into the system. Also, the second one is vaporization of liquid. When you have liquid, when this ice changes phase from solid to liquid, when you further increase the rate at which it is being supplied to the system, what happens to the liquid? The liquid becomes what? It becomes vapor or gas. Are we together? Then the third one is mixing of gases. And the fourth one is free expansion of gases. How does free expansion occur? This occurs when heat is being input into a given system. And lastly, heat flow from a hot substance to another fluid. These are some of the examples of when you have a processes that increase entropy in a given system. Now, the reverse is the case for process that decreases entropy in the case. You know, we mentioned melting ice. In process that decreases entropy in a given system, what are we going to do? We are going to freeze the liquid back to what? Ice. That's one example. The second one is compression of gases. You know, we make mention of expansion of gases when we are talking about a processes that increases entropy. And lastly, condensation of vapor. When you have heated water and the water has gotten to vaporization state, when you go back and cool the water by applying a condensation into it. If you go back to your refrigeration and air conditioning, where you have your refrigerant, when it passes through the major components of the refrigerator setup, the refrigerant, when it moves from the condenser, it's coming out as a particular phase. When it's leaving the condenser into the evaporator, it's occurring as a particular phase. So those are some of the key features of entropy. What are the practical importance of entropy in engineering? Practical importance of entropy in engineering. Number one, it is used to analyze the efficiency of engines, turbines, compressors, amongst others, etc. The second practical application of entropy is that it helps identify losses. It helps identify losses in real system. The third one, it is essential in understanding reversible process versus irreversible processes. And the fourth one is that it is crucial in designing refrigeration and power cycles. These power cycles come in two different forms. We have the vapor power cycle and we have the gas power cycles. Some of the examples of entropy, I have mentioned it earlier on. When you melt ice, it becomes what? A liquid. When a gas expands or a gas compresses, that is another example of an entropy. Now, let's look at entropy change in different processes. Now, entropy change occurs in about 8 different processes. The first one is some of the things that we have learned so far. We have learned about isothermal, isochoric, isobaric, adiabatic, polytropic, and so on and so forth. So we are starting with isothermal process. Don't forget that the mathematical expression of an entropy is defined as change in S equals to change in Q over T. That is the mathematical form of an entropy. And in an isothermal process, which is the first one, in isothermal process, which is a constant temperature process, the entropy in this case is given as change in S equals to mR ln V2 over V1, which is also the same thing as following Boyle's law, PV equals to C, making P1 V1 equals to P2 V2. So you have V2 over V1 equals to P1 over P2. So this expression can also be written, if this one is equation 1a, it can also be written as change in S equals to MR ln P1 over P2. That is the first case for an isothermal process. The second one is isochoric process. An isochoric process is a process in which the volume is held constant throughout the process. So what happened in this case? In isochoric process, we believe that it's a form of an expansion and a compression process, whereby the volume remains constant throughout the process and the pressure changes from state 1 to state 2. The second process in which we are analyzing entropy change is in isochoric process. And as we all know that an isochoric process is a process in which the volume is held constant throughout the process. So the entropy change in this case is given mathematically as change in S equals to mCv ln T2 over T1. The third one is isobaric process. For an isobaric process, what happened in this process? The pressure remained constant throughout the process. And the mathematical representation of an entropy in this case is given as change in S equals to mass multiplied by Cp ln T2 over T1. This is for isobaric process. We want to look at entropy change in adiabatic, reversible adiabatic process. An adiabatic process is a process whereby it is not allowed to come in and leave the system. It's a system that is thermally insulated. So in this case, what happened? Where it does not allow, when we have the mathematical expression of entropy to be written as change in Q over T. When it is not allowed to come in or leave the system, what happens to Q in this case? Q becomes 0. So the entropy change in adiabatic process is 0. However, in an irreversible adiabatic process, the entropy change is defined as change in S is greater than or equal to 0. This is for irreversible adiabatic process. And the first one is for a reversible adiabatic process. Irreversible adiabatic process. The fifth one is entropy change in a polytropic process. You should recall that any form of equation that comes in this form, PV raised to the power of n equals to C, such expression is referred to as a polytropic process. Now, what is the entropy change in this system? The entropy change in this system is given as change in S equals to MR ln V2 over V1 plus MCV ln T2 over T1. So this is the entropy change that occurs in a polytropic process. And the sixth one in phase change. Phase change. What is the entropy change that occurs in this system? This one is very easy. Change in S equals to our normal change in Q over T. Don't forget there is a particular problem that we solved when we were trying to treat example on heat transfer, where we make Q to be equivalent to entropy. Can we recall what I just said? So in this case, for phase change, we are going to replace change in Q with change in entropy. But that entropy that we are talking about is the entropy that lies between the saturated and the superheated stage, which is given as MHF of G over T. That is change in entropy for phase change. Change in entropy in an ideal gas. We all know that any form of equation that follows the relation of PV equals to what? RT. That takes the shape of what? An ideal gas. So therefore, the entropy change in ideal gas is change in S equals to MR ln V2 over V1, which is also the same thing as MR ln P1 over P2. The last one, we are going to look at the entropy change in heat transfer across a finite temperature difference. And the entropy change is expressed mathematically as change in S of the total system equals to change in S of the system plus change in S of the surroundings. In this case, is greater than 0 when we are trying to consider for a finite temperature difference. Now, let's solve some simple problems before we now graduate to more complex one. Let's just solve two simple problems. Finite temperature difference. Example 1. A sample of 2.0 mole of an ideal gas expand isothermally at 300 Kelvin from an initial volume of 0.01 meter cube to a final volume of 0.02 meter cube. Full stop. Determine the change in entropy of the gas. In the question, let's analyze the question. Let's solve it. The first thing is, the first step you are going to take is write out the given data. The first one, we are given number of mole, which is 2.0 mole. We are given temperature, which is at 300 Kelvin. We are given V1, which is 0.01 meter cube. And when it expands, it goes to volume 2 at 0.02 meter cube. The second step is to define unknown. Fine. We are asked to determine the change in entropy. The third one is assumptions or engineering model. Assumptions or engineering model. Assumption 1. The gas is modeled as an ideal gas. That's assumption 1. Assumption 2. The gas expands isothermally, which means the temperature remains constant throughout the process. Those are the two assumptions that we can bring out of the question. Then the next one is, what is the governing equation? The governing equation is change in S equals to NRU ln V2 over V1. This is the governing equation in this case for ideal gas. Now, the first one that we have always been familiar with is change in S equals to MR ln V2 over V1. You will notice that the R that you have here is known as the universal gas constant. Why this one is ordinary gas constant? I think we have done something on this and I have done justice on it. How do we arrive at this? Go back to the previous lecture that I taught you. You are going to get more information about it. Let me just simplify it. R, the gas constant, is defined as the universal gas constant divided by what? The molar mass. Then also, number of mole equals to mass over what? Molar mass. By the time you do your mathematics, you will discover that this expression can also be in this form. However, mass is not given in the question. We are only given mole in the question. That is why we are adopting this equation. So what is the next step now? Is to analyze the problem. Analysis. The entropy change during the process is given as N R ln V2 over V1. The next thing we are going to do is to insert values that are given in the question. Therefore, change in S becomes, the number of mole is given as what? 2.0. 2.0 multiplied by the universal gas constant, which is 8.314 times 8.314 multiplied by ln V2 is given as 0.02 divided by 0.01. By the time you punch your calculator, the result becomes 11.53. 11.53 joule per Kelvin. That is the final answer. So let's take another example. Example 2. Determine the change in entropy of air, if it is throttled from 0.8 megapascal, 30 degrees Celsius to 0.3 megapascal adiabatically. Take the value of Cp equals to 1.005 kilojoule per kilogram Kelvin and R for the gas constant of air to be 0.287 kilojoule per kilogram Kelvin. Solution. Now let's bring out the parameters in the question. The given data. The initial pressure is given as 0.8 MPa. Temperature T1 is given as 30 degrees Celsius. The final pressure is given as 0.3 MPa. Since the process is throttled, therefore T1 equals to T2, which is 30 degrees Celsius. Then the second step, before we move to the second step, we are given some constants. Cp for air, 1.005 kilojoule per kilogram Kelvin. And we are given R to be 0.287 kilojoule per kilogram Kelvin. Then the second step, we should define the unknown terms. Find change in entropy of the system is what we are asked to determine. Then the third step is to bring out the assumptions from the questions. The first assumption is air is modeled as an ideal gas. Air is modeled as an ideal gas with a constant values of Cp and R. The second assumption is that the temperature is constant during the throttling process. The temperature is constant during the throttling process. And the third assumption is change in kinetic energy and change in potential energy effects are negligible. The governing equation. Change in S, which is the same thing as S2 minus S1, equals to Cp ln T2 over T1 minus R ln P1 over P2. So the next thing we are going to do now is to impute some of the values that are given in the question. Cp is given, R is given, temperature is given. So let's insert it into the governing equation. Analysis. We want to start analyzing the problem. Change in S becomes Cp 1.005 multiplied by ln temperature T2, that's 30 plus 273 over 30 plus 273 minus R 0.287 ln P1 is given as 0.8. You have to be very, very careful in this case. This P is in mega, while R and Cp, they are in kilo. So the SI unit must be uniform. So you have to take this gentleman to kilo. So multiplying it by 1000, we have 800 watts kilopascal. 800 over 300. So by the time we punch our calculator, the result becomes 0.281 kilojoule per kilogram Kelvin. That is the answer. The value for entropy change in the given calculation is negative, as change in S equals to S2 minus S1 equals to minus 0.281 kilojoule per kilogram Kelvin. Therefore, X1 minus S2 equals to 0.281 kilojoule per kilogram Kelvin. Do you understand now? Example 3. On the basis of the first law, fill in the blank space in the following table of imaginary heat engine cycles. On the basis of the second law, now classify each cycles as reversible or irreversible process. The table is given below. So we have 4 cycles. We have cycle A, cycle B, C, and D. For A, we are given the source, the temperature. We have 2 things here. Temperature, under the temperature, we have the source and we have the sink. The rate of heat flow, heat is being supplied and heat is being rejected from the system. Also, we have the rate of work output. All the values are given in the question. And the next one is the efficiency. And the last column is the maximum efficiency. Before we solve this problem, I have to explain some things to you. The first thing is, in a heat engine, the net work output, it involves 2 things. The first one is you must have the source. The source is where the temperature is being added to the engine itself or the system. Why the sink is a form of temperature loss from the system. A typical example of a heat engine is when you have something of this. This is the engine, and this is where the work is being done. And we have here to be the source, here to be the sink, depending on the arrow. This is the sink, TL. At this point, the temperature is lost. And at this point, we have the temperature to be added to the system. Also, heat is added to the system at this level, and heat is being rejected from this system to the surroundings or environment. This is a typical example of a heat engine. So how do we derive some things out of this? Some of the things that we need in calculation. Number one, the network output is given as QH minus QL. Master this equation. We are going to use it. The second one is the efficiency of the engine, of the heat engine, is given as the net work output divided by the heat supply to the system. That's another one. This is for the efficiency of this. We are going to make use of this. Then we also have maximum efficiency. For maximum efficiency, anytime they are talking about maximum efficiency, they are talking about an ideal cycle, which is known as the Carnot cycle. I think that is what we are going to be looking at in our next lecture, where we'll be talking about different cycles that we have in thermodynamics. So for this, for the maximum efficiency, we'll refer back to the Carnot cycle, where you have the efficiency to be TH minus TL over TL. So we are going to make use of this mathematical representation. Now, how do we go about this? We want to start solving now. Let's look at cycle A. In cycle A, we are given the source temperature to be 350. We have the sink temperature to be 30 degrees Celsius. You will notice that the sink temperature is far lesser than that of the source temperature. Then the heat supply to the system is given as 500 watts, and the heat rejected from the system is 350 watts. We are asked to determine the rate of work output, the efficiency, and the last one is the maximum efficiency. So following the normal problem solving techniques, list out the given data, tell us what you are asked to determine. That will be step 2. Tell us what you are asked to determine in the question, which are 1, 2, 3. The next one is bring out your form of assumptions. Then the next one, bring out a schematic. I think I have brought out a schematic, which is this. And lastly, your governing equations are this set of the mathematical expression that we are going to be using in solving this problem. Now, let's start analyzing. So, for the cycle A, we are asked to determine the rate of work output. Now, from all the expressions that I've given on the board, how are we going to determine this? The rate of work output, which is given as Q supplied, QH minus Q what? Rejected, Q loss. And Q added to the system is given as what? 500 watts. And that of rejected is given as 350. So by the time you subtract 350 from 500, we have 150 watts. So we have gotten this as 150 watts. The next thing is to determine the efficiency of the system. Note, the ordinary efficiency in this case, we are taking this expression to use to determine it. When we are talking about the maximum efficiency, that is when they are talking about maximum, from the word maximum, which means the efficiency at this level will be higher than that of this level. Now, let's go for the efficiency. Efficiency is what? The net work output divided by what? the heat supplied. The network output is determined to be 150 watts divided by Q supplied 500 watts. Watt cancel watt, 0 cancel 0. 15 divided by 50. What's the final answer? 0.30. That is 30%, which means the efficiency of cycle A is 30%. Now, the next one that we are asked to determine is the maximum efficiency. And the maximum efficiency is determined using this equation. The temperature added to the system at the source minus the temperature at the sink divided by the temperature at the source. So therefore, we have TH is given as 350. If you like, you convert it to Kelvin. Please convert it to Kelvin before solving. 350 plus 273, what's the value? 623. 30 plus 273, 303. Then divided by 623. When you subtract this, what do you have as the maximum efficiency? 0.514, which is 51.4%. So here we have it as 51.4%. So we are done with the first cycle. Then the second cycle, in this case, we are given the source temperature, we are given the sink temperature. We are asked to determine the rate of heat supplied to the system. We are given that of heat rejected. Then also we have to determine the rate of work output. The normal efficiency is given, and we are asked to determine the maximum efficiency of the cycle. So now let's move on. For the second cycle, we are given the source temperature, the sink temperature, the rate of heat flow that is being rejected is given, the efficiency is given. We have three unknown here. The rate of heat flow that is supplied into the system, the rate of work output, as well as the maximum efficiency. These are the unknown terms that are given in the question. So now let's go on. How do we get this value? So we go back to the normal efficiency, which is the network output divided by what? The heat supplied to the system. We are given the efficiency to be 68, which is 0.68 multiplied by QH is unknown. QH is unknown. QH is unknown equals to the rate of work is also what? Unknown. And that one can come in as QH minus QL. So what are we going to do now? Take this gentleman here and take this one in. So QL, which is given as, QL is given as 5.2 megajoule per minute. So we need to take it. Don't forget what we are asked to calculate the value. We are asked to leave it in terms of what? Kilojoule per second. So we have to reduce this M to kilojoule. So we multiply it by 1000. We have to also reduce the minutes to seconds by multiplying it by 60. So what are we going to have? 5.2 times 1000 times 60. What is the value? What? 312 123. That is QL, which is the same thing as QH. That is 1 QH minus 0.68. 1 minus 0.68. 0.32 QH. So divide both sides by 0.32. 0.32. So QH becomes 9975123. What is the units now? The units now is in what? Kilojoule per second. So 975. So 975,123. So we have gotten the heat supply to the system. The next thing is to determine what? The network output. Don't forget, the network output is QH minus QL. So QH is 975,123 minus QL 312,123. So the answer becomes 0.00366. Am I right? So the units, kilojoule per seconds. So substitute it into the table. 663,123. So the maximum efficiency in this case, the maximum efficiency becomes TH minus TL over what? TH, which is the same thing as 1 minus TL over TH. So we have 1 minus TL is 150 divided by 990. So what is the maximum efficiency in this case? Zero point eight four eight. 0.848, which is equivalent to 84.8%. You can see that the efficiency, the maximum efficiency is greater than this, 84.8%.